Good morning, everyone.
Good morning.
We're up to 7 people in the class. We're supposed to have 12, if I remember correctly. Yeah, still 7. And while we're waiting for everybody to arrive, does anyone have any questions on anything? Okay. Well, I want to tell you this, since class time has already started, go ahead and remind everybody. The syllabus is up. Actually, I didn't put a change on it yet, so it still shows that erroneous date for the midterm. But I will put it up today right after class, or maybe even during lab. Uh, but like I said, I'll put it up, and I'm showing on that the new version that we're taking all of a whole 2 class days. In other words, this whole week on chapter 23. That's pretty normal. Sometimes the chapter that's the more difficult one or covers more material, I have to spend a little more time on. So I've been plotting basically a chapter or 2 chapters a week, but I made enough room where, there's more than enough days to cover 2 chapters a week, if we're literally keeping up that pace. So I've got a little playroom, so I decided to make chapter 3 one of the ones I take more time on. I did put up practice test 1 and 2. I think y'all saw that last time. I also put up actual test 1, which isn't due until the 14th. Okay. But tomorrow's the drop add date. Well, drop add, not with getting some tuition back. Let's put it that way. So some students would like to see how they're going to do or whatever before that date, at least have one test or something like that. So I went ahead and made the test available. So y'all can take it all 3 attempts today if you wanted to, but you're not really required to till the 14th. That being said, if you don't set an alarm on your clock, on your phone or something to tell you, hey, come back here and take this test on the 14th, you're liable to miss it, and that's going to be a 0. Missing an online test is a bad thing. Missing any test is a bad thing, but missing the online test means the one grade that I'm going to drop, it's now that one. So unless you have a valid excuse like you're in a bad verifiable car wreck or death in the family, again, verifiable things, then I can't just let you take it because you just weren't ready or weren't or forgot to do it. So make sure you guys go ahead and get that test done. You might just take it, 1 attempt today. It's on chapters 1 and 2. You've probably done most of your homework from chapters 1 and 2, so you should be in a good spot to take it. But I'd at least take one hit, so that way you won't get a 0 even if you forget it. Otherwise, make sure you set your alarm and then reset it until you actually take it. And it's due on the 14th, according to the schedule and to what I made it. So make sure you guys get that done. Oh yeah, since we're doing 1 chapter this week instead of 2, that means chapter 4 obviously is not ready to be turned in by Monday, so I'll be moving those dates back as well. So we're now up to 9 people in the class. So I guess I'll ask one more time. Does anybody have any questions on the course or any past material or upcoming material?
Sorry, my internet
anything related to physics, basically.
Before you talked about chapter 4, what did you say?
Yes, I'm going to push chapter 4 due date back because we're not covering chapter 4 this week.
Before that.
What's that now?
Before you talked about chapter 4 and the homework. Something
Oh,
about
I mentioned the practice test.
Practice test. Okay.
The practice test is already available. Actually, the first 2 practice tests are already available, and the actual test the actual test 1 is already available, and it's due on the 14th. And I suggested people at least do it sometime today or tomorrow just to get 1 test in. But also, I put it up to make sure everybody had a chance to get a graded test done before the drop date. people don't drop my class, but I still feel obligated to try to get some robust grade back to them before that date, just in case they, say, oh, this is too much for me. So you'll see an online test, which honestly is the easiest of the tests because you're allowed to do internet searches, even though you got limited amount of time. You're allowed to do open book, open notes, open other books, open other people's notes, provided those notes were not created since the actual test opened up. Because once the actual test opens up, other students can come in and even though each student's going to get a slightly different test because it sort of chooses from a set that I said were basically all equivalent. It's still some overlap, and because of that overlap, you give everybody a disadvantage if you told them what you did and or what you experienced on your copy of the test. So if anybody makes any notes after this morning at 1 a.m., none of those notes can be shared. If anybody makes a website after 1 a.m. this morning, none of those websites can be looked at. So that's just just showing, hey, you can use whatever's already out there, just nothing that's been created since I put the test up, so that we can't get any back communication. Obviously, you can't talk to someone for help other than me. You can't talk to them via text, via Skype, or anything like that. You just have to take the test on your own with your own resources and stuff you can find on the internet that wasn't created since that date. Okay. Anything else? Well, since, like I said, there's online testers, so quote unquote easy, you can see they don't count as a huge fraction of your grade, but you are allowed 3 attempts every time. The practice test counts half as much, even though the practice tests are actually just extra credit. They're worth up to 5%, which means if you had a perfect 100 on all of them and you didn't skip any of them, then you get 5 points added to your course grade. So I'm recommending you take them, because the more you take them, that's really good preparation. It's basically my way of trying to get you to do like I did when I took these courses. When we took these courses, people old like me and people way older than me, they normally had, the instructor would give them maybe 10, 12, 20 problems out of the back of the chapter for each chapter they cover, and we work them, and the students would ask questions if they had any, but we never turned them in to be graded or anything. But when we were trying to do those, we ran into problems, so we ended up, like me, I would try to solve every odd one at the end of each chapter, and eventually I managed to solve, in fact, not every odd one, but every other, everyone, period. Not as an undergraduate student still, but I did do it. Now, in order to get you to do all those problems, I got to give you points. So I do a homework set that's sort of the low hanging fruit. It's got some tying problems, some that are more difficult than normal, but it's really not very much. So the onus comes down on you to do a lot of problems by you just taking the practice test. So if you're taking the practice test, the more times you take it, the more problems you're solving. So it's just like me when I used to solve extra problems for my own help. So hopefully you guys will learn that we don't do homework as punishment. We don't do homework as busy work or anything like that. Our homework, especially in the physics and chemistry, the physical sciences, the homework is really, really about you figuring out how to do solving problems and making you prepared for the test. So even when you have a class that don't have homework graded, I highly recommend you take it. You do a lot of homework. Okay. Anybody else? All right. So that's the rundown on that. Like I said, I'll be when I put up a new syllabus, it'll have the same name as the old syllabus, but at the end of it will have a date, and that date, this case will be 6/02. I think it's 6/03, so it's June 3rd. And whenever you look at the list of syllabi, the one with the latest date will always be the most current one. So I'm not really allowed to make major changes. Like I can't go back now and change the percentages that I allot each of the tests and all that stuff. Those are big changes. I'd have to get all your agreement, because we had a contract that was the syllabus. And when I introduced that to you on that first day, I was sort of locked into those grading principles. Any changes I made have to be made before July 3rd, before June 4th. But if I make any after that, that's when I have to get more or less permission from y'all. Except for, like I said, where I told you that the schedule is tentative, I can make that change any time of the day. And I don't even have to necessarily tell you. I just, you just know it because what you've covered. All right, so I guess we'll go ahead and jump into chapter 3. And like I said, we will finish up chapter 3 today, but I'm hoping maybe I'll even get into chapter 4. So we're studying projectile motion. I told you how you could do that cool vector function for a projectile. We'd say r vector, we just call it r with a vector symbol over it, is equal to x of t I hat plus y of t j hat plus z of t k hat. And we could normally say, for instance, let the x come in and out of the plane of the paper, say, and then y would be to the right and z would be up. So that in that case, the x-axis or the I unit has nothing. What I'm going to do now is solve one generic problem, but solve a bunch of different parts of it. So you'll get these nice general expressions that apply to all situations of projectile motion, provided they take off and land at the exact same height. So if you're shooting something from a cliff down to the ground, or something from the ground up to a cliff, or if you're even kicking a football from a meter above the ground and it lands on the ground, all bets are off. These equations don't work. They come close because they tell you, for instance, the amount of time for the ball to get from 1 meter high to 1 meter high again. Obviously, when the ball has been kicked a long distance and stuff like that, if whatever time it takes to go that last meter vertically is going to be a very small fraction. So it's not going to go that much further long ways horizontal, or that much take that much more time. So it still gives you a rough estimate of what it should be. But if you want to actually work it out properly, you're going to have to do all the stuff from scratch. So let me go ahead and turn my document cam on and show you how to do that. We've already talked about relative velocity, so I'm not even going to solve problems in that section, even though I do consider that section 3.9 important. So you should know those examples. Those examples are more or less the simplest scenario. And you'll see in the homework, I've got one with a couple different variants in it. So that'll be a really good chance for you to do a relative motion problem. All right, so what I told you before was, because of that cool diagram on page 63, we saw that when a ball is shot horizontally, or when a ball is dropped vertically from the exact same height at the exact same time, we find that the balls fall at the same rate. In other words, if you took a snapshot at 0 seconds, both of them would be the same height because we've dropped them and shot them horizontally from the same height. If you took a shot at 0.01 seconds, they'd still both be at the same height, but it's now a different height because the one's been shot and the other one's been dropped. If you do 0.4 seconds, 0.04 seconds, they're going to be at the same height again, but again, a different height. So that the actual vertical motion, gravity, that gravity is causing, is independent of what's going on horizontally. So you can really treat those motions separately. And that's the crux of understanding projectile motion problems. So if you want to, for instance, say how far you can throw, one thing you're going to have to do is think about, okay, well, how tall am I? And if you're, a minion, that'll work pretty well. So like if you're, 2'8", that's really easy, because the difference between a 2'8" tall person and the ground is only 2'8". So you're not going to get that bad result by assuming they left and landed at the same height. But in practicality, we aren't going to be that way. So what I'm going to do is imagine firing a projectile horizontally, at some angle above the horizontal, and allow it to land at the same height. And if I want to figure out how far it's going to land away, I just have to figure out, okay, well, because I shot it at some angle other than horizontal, it has a x and y component. That x component is just going to be, since we ignore air resistance, it's just going to be something moving with a constant velocity. So that's sort of like if you imagine the sun was directly overhead, it's how fast is the shadow going across the ground. Well, that turns out just to be the horizontal component of velocity. Then all that matters is how long your vertical component of velocity allowed it to stay in the air, because that's how long it's going to get to go to the right, say, before it hits the ground. So if you want to figure out how far it'll go, in other words, what's called its range, then you're going to take basically figure out how long it can stay in the air. So for instance, I worked a problem before where it was 58.8 meters per second upward. Well, that happened to be 6 times 9.8. So I knew it was going to take 6 seconds to go from leaving the ground to reaching its max height, because that's where the velocity reaches 0, because each second it decreases its velocity by 9.8. And then it'll fall another 6 seconds back down So I know that 12 seconds is the time aloft if the vertical component of velocity is 58.8 meters per second. Because of that, if the horizontal velocity is say 20 meters per second, then all I have to do is take 12 times 20, because it's 20 meters per second is the horizontal component, and 12 seconds is the time that the vertical velocity allowed us to stay aloft. Then 12 times 20 gives us 240 meters. So that's how you solve a projectile motion problem. The problems I can ask for are how long will it be in the air? How long will it take to reach its max height? What is its max height? How far away it will land? What's its final velocity when it does land? And then, of course, what are the components of the final velocity when it does land? So those are all the different things you can ask about projectiles, and you don't always have to fire them from the same height that they land on. And we'll work some problems like that. But I'm going to start off with that generic one. So let's consider our axes that I told you about before. Actually, I'll go ahead and say bump the z-axis. I'm just going to call this x, and I'll call this one y. So it's more like normal. Okay. What I'm going to say is that the projectile was shot from the origin with a velocity v0 at an angle theta. Okay, so that means the magnitude of the velocity is just v0, and the angle between the horizontal and the angle of the cannon tube, basically, which ends right here, that angle is theta. What we know is going to happen with that motion is, as I showed you before, and hopefully you verified yourself, it's going to create a parabolic trajectory. And way down here is what we call R, the range. That's how far it can make it for a given angle and a given muzzle velocity. This right here is called H max. Okay. This time right here is considered T max. And of course, this time here is T equals T total. Okay. And of course, when it lands, it will have some velocity V at some angle phi, say, with the horizontal. Okay, so there's a lot of junk in that little diagram, but what I'm saying is this angle right here is phi. This vector, this final velocity vector, is just plain V. Okay, and it has a horizontal and a vertical component. That's why it has an angle phi associated with it. So all these things I could work out. As I told you before, we could start with the idea that R, the position vector as a function of time, is really just x of t I hat plus y of t j hat. Before I had mentioned x coming out of the board, and then it would be y to the right and z up. This one I'm just using x and y. We know since there's no air resistance, that's a big assumption we're making here. No air drag, no air resistance, no friction, say, between the air and the ball or whatever that we're firing. So with that, we know the only acceleration is the acceleration due to gravity, and that acceleration due to gravity is a constant g downward. I've drawn the upwards y direction as the positive y direction. So clearly the acceleration is going to have to be in the negative direction, and it's going to have a value of 9.8 in magnitude. Since this thing doesn't have any acceleration, and since we started from x0 equals 0, we can use the equation x equals x0 plus vt, which is for average velocity. But that average velocity, since there's no air resistance, is the x velocity period. So I'm just going to write this as, since x0 is 0, I'm just going to write it as v0. Now I've got to take this and I actually got to make it into an x and y component. So I'm going to say this x component right here is v0 sub x, and this y component right here is v0 sub y. I think you can see from this diagram, v0, v0y, v0x, that v0x, if this is theta, which it is equal to v0 cosine theta, and this one's V0 sine theta. So I'm just going to say the x component is V0 cosine theta. Okay, that's going to be multiplied by time because that is our average velocity. That actually happens to be our velocity period. Okay, again, horizontally though, it's the resolution of it in the x direction. So I could put an I hat in front of that. Now I have the x of t I hat. So this is what x is doing as a function of time. At t equals 0, I get 0 times all this. It's at the origin. That's what we expected. The y of t, on the other hand, the y of t is going to have a negative 1/2 g. That looks like a long fraction bar, so I'll put a negative 1/2 g times t squared, plus it's going to have the initial position, which would be y0, but I said that was the origin, so that's going to be 0. And it's going to have the initial velocity times time. So the initial velocity in the vertical direction is v0 sine theta times t. I'll put that in parentheses again so you don't think I'm taking the sine of theta times t. And then plus y0, but again, like I said, y0 is actually 0. So I'm going to put a square bracket around this and call that all j hat. Just like I could put a square bracket around this and call that I hat. Okay, so this is a function. This is a vector function that gives you, if you plug in time, assuming you know v0 and theta, if you plug in all these values, this will give you a vector that points to projectile at any point in time. If you wanted to know the velocity at any point in time, you just say v of t is equal to dr over dt. And of course, you can see what happens with that. When I take the derivative of this with respect to time, it's just going to be v0 cosine theta in the I hat direction. And then in the j hat direction, this derivative is going to give you v0 sine theta, but this one's going to give you negative gt. So I'll say plus v0 sine theta minus gt, and that's the j hat direction. And remember, I told you the total acceleration, which I'll call a of t just to be generic about it. The total acceleration is dv dt, which is also d2r over dt squared. I just take the derivative of this. Obviously, there's no time dependence in there, so I get 0 I hat. There's no time dependence in there, so that's a 0. So all I really get is negative g j hat, and that's exactly what we expect. That's really what is happening is the projectile is going along here. At every instant, its acceleration is 9.8 downward. Every instant, even right here. Yeah, the velocity is 0 there, but you can have, and this is a big conceptual idea, you can have a velocity being 0 and have actual acceleration. You can have a velocity that's 0 and have no acceleration too, or you can have a acceleration that's 0 with a 0 velocity. So there's all these different ways you can do it, but a lot of people seem to think that the velocity, or excuse me, the acceleration changes from here to here, and then from here to here it changes again. No, it's just always negative g. Again, assuming we ignore air resistance. Okay, so that's really the solution in some sense to all projectile motion problems. If you wanted to make it more generic, then you could add plus x0 in the side of this bracket and plus y0 inside of this bracket, so that you don't have to fire it from the origin. That's fine too. But you can really do everything you need from this. I'm just not, and most people don't do it this way. So I'm not going to do it this way. What I am going to do is say, let's find, I would like to find the range. I would like to find V final. I would like to find T max. I would like to find T total. And I'd like to find H max. And I think that's about it, really. I figured out how long it is, how high it goes, how far it goes. Yeah, so that's basically all the possible things they're going to ask you about projectile motion. On a given projectile motion problem, they probably could ask you any of these 5 or all of them or whatever. So how do I do it? Well, first thing I'm going to do is figure out what T total is. And I can also figure out T max and just double it, because from the symmetry, when the projectile leaves and lands at the same height, you can see it must take exactly as much time to reach the max height as it does to go from the max height to the total time. So clearly, this T max is 1/2 of the total time. You should really convince yourself of that once, though. So I'm going to just work out T total. So T total is going to be solved this way. So what I'm going to do is I'm going to say a projectile is fired upward with a velocity of v0 sine theta. And what I want to know is at what time does the y component of velocity equal 0? Well, if I look at this, or if I just take one of my kinematic equations, for instance, v equals v0 plus at, if I took that equation, I can see that v final equals 0 would give me the T max. But I don't want that because I'm wanting to solve for T total. But that is a way you can do it. Once you've proven to yourself that T max is in fact half of T total, you can do that. What I want to do is figure out, well, at what time is my Y height going to be equal to my initial Y height? In other words, when is Y equal to 0? So I can set all this right here, which is, again, just a kinematic equation. I can say Y equals negative 1/2 g t squared plus v0 t sine theta. That way I don't have to put the parentheses there. And I could put plus y0 here, but I already know y0 is 0. So what I want to do is say, let's let this equal 0. This one would get. So I didn't do it that way because this one just would help me to find T max, because the y component of velocity, v0 here being v0 sine theta, with the y component of velocity equaling 0, you can see that means it's not going to get any higher, because if the velocity was positive, it would go higher still. If the velocity was negative, it has already moved past this, because just a second ago it had 0 velocity. So this is a way you could do it, but like I said, that assumes that we are going to use a symmetry that you haven't convinced yourself of yet. So I'm going to take and say, when does this y value equal 0? One obvious answer would be when it initially took off. And this equation will tell you that. So I'm going to say, set this equal to 0. Notice this side's negative. This term's negative. This one's positive. So I can just put them on opposite sides of the equal symbol like this. And that's equal to v0 t sine theta. Of course, what I could have done beforehand is I could have went ahead and factored out t. And if I did that, it would have been t times negative 1/2 g t plus v0 sine theta is equal to 0. And what you'd see here is when two numbers multiply, remember this is the whole reason you learned about factoring in algebra, is one of the big reasons was that you could solve equations after you factored them. So once you get a string of factors multiplied by each other equal to 0, you know each factor could be 0, and that's a valid solution to the equation. So t equals 0 is one time, but that we already knew. The other time, however, is when this factor is equal to 0, which is what I get here, because if I wanted to, I could divide through by t on both sides. I'm obviously taking the case where t is not equal to 0. So I divide through by t on both sides. And just like this, if I solve this for t, you'd see t would be equal to basically 2v0 sine theta over g. And you can get that here as well. This means t total is equal to, again, I'm solving for this t over here. So this 2 is going to multiply by v0 sine theta. So I'll say 2v0 sine theta. And then I'm going to divide it by g. And that is, in fact, the total time that it's in the air, 2v0 sine theta. So if I threw it straight up, theta would be what angle? Anyone? If I threw the projectile straight up, what would the angle theta be?
$90.
Yes. Cameron gave me an answer. Thank you for answering. So yeah, it would be 90 degrees. And of course, the sine of 90, this is one of those things that your instructor is going to be a pain in the butt about. The whole semester, I will assume you know everything you've ever learned in every math class that you supposedly had taken. And one of the things I expect you to know is the graph of sine looks like that. And the graph of cosine looks like this. And this is 2 pi, and this is 2 pi. So you see at pi over 2, sine is 1. So it's sine of pi over 2, which is right here, which is 90 degrees, sine is 1. So this just becomes 2v0 over g. Well, earlier I told you about using v0 as 6 times g. Remember I said it was 58.8, because if you multiply 9.80 times 6, you'll get 58.8. So in here, if I took 2 times, just thinking of the magnitude now, think about it, I would use 2 times v0, which I said was 6g. So that'd be 12g divided by g, that's just 12. So in fact, you would get 12 seconds, which is exactly what we worked out before, is that a projectile fired upward at 58.8. I'm talking about during lab, of course, guys, when I did this stuff, those of you who had me for lab. When I did 58.8 in the vertical motion in the Excel spreadsheet, I found that it took 6 seconds to get to the top and then 6 seconds to get back down. So the total time was 6 seconds. This result agrees with that. So by using theta equals 90, you can attack, with this generic problem, you can attack exactly times for throwing straight up as well as throwing straight down as well as throwing horizontally. So I've got that. Now let's look back at this one and say, let's be dumb and just see if we can solve T max. Okay, we're going to pretend like we don't know from symmetry it's already exactly half of this answer, right? I'm going to just work it out. And the way I'd work it out is I would take this velocity as a function of time, which you can look at as just v equals v0 plus at, which is just this. The a happens to be negative g, and the v0 happens to be v0 sine theta. So I'm going to say v y is equal to v0y plus ay times t. That's our kinematic equation. I just put y subscripts on everything, so you know I'm talking about y motion. What I want to do is figure out when vy is equal to 0, that implies t is equal to t max. So I'm going to say 0 is equal to v0y, which is just v0 sine theta. Okay, and of course ay is negative g, so I'll say negative g t. Now if I solve for t, you can see what's going to happen. I'll pull this g and t over here, it'll become positive, and t just becomes v0 sine theta over g. Notice that is exactly 1/2 of t totals. If I multiplied this by 1/2, that 2 would cancel out and I get exactly that formula. So there's another nice expression. And trust me, if you actually go through the time, the work of working this out yourself without, me prodding you along and telling you what to do, if you look at this, figure out how I'm doing it, then do it yourself, you'll probably have these formulas memorized. So it's actually, not that hard to do that stuff. So now I've got T total, I've got T max. Let's put little check marks on that. Woohoo, Mr. Younger's 2/5 of the way there. Let's say I want to find the range. Well, the range is easy enough. This is where I told you about the fact that you can treat the horizontal and vertical motion completely separately. I now know, for instance, because I have T total, I know how long the projectile is going to be in the air. So I know it's going to move at that horizontal velocity, V0 cosine theta, for that whole period of time. So in fact, all I have to use is this equation right here because the initial position is 0. In other words, I'm using x is equal to x0 plus v bar t. And this time I'm actually using x's instead of y's. So in this case, since the v is a constant because there's no air resistance, then the average v and the v are the same thing. So this is going to become r is equal to 0 plus v0 t cosine theta. Notice I put the t between them so it wouldn't be any ambiguity about the cosine acting on the t or not. All that is my x as a function of time. And what I'm saying is this has to be evaluated at t equals t max in order for x to be r, the range. Okay. So now all I have to do is plug in that and I'll see that r is equal to v0 cosine theta. My t max, of course, is 2 v0 sine theta. And then over g, of course, so I got that. So my range is actually 2, I said 2 down here. This is supposed to be a g. I don't know why I wrote a 2. Okay, so it's 2 v0 squared sine theta cosine theta over g. Now, does anybody recognize an identity that's 2 sine theta cosine theta? Nobody remembers that? Okay. Cosine of 2 theta is actually equal to cosine squared theta minus sine squared theta. That's one way you could look at it. Another way is you could realize that 2 sine theta cosine theta is actually equal to, I want to say, sine of 2 theta. Let me double check that though before I jump along too far. Not there, not there. Still don't see it. Still don't see it. I need to check my trig identities, I reckon. Yeah, I must have did that. Let me check my trig identities in the back of the book just to make sure. Like I said, I just don't. If it was cosine of 2 theta, then when theta equals 90 degrees, it'd be cosine of 180. And that would give me a -1 for that. So that wouldn't make any sense. So I'm about 99% sure that 2 sine theta cosine theta is actually equal cosine of 2 theta. And I just did that using the physics of what I know should be right. And that's really enough to convince myself that 2 sine theta cosine theta is the sine of 2 theta. But just to point out exactly where I'm getting that identity from, in case you don't recall it, I'm going to go ahead and find it in the appendix of your book, which has a lot of nice little answers or nice little identities and integrals and stuff like that. So more on dimensional analysis, didn't want that. Derivatives, integration by parts, a few definite integrals. Here's my trig identities. Yes, the sine of 2 theta is equal to 2 sine theta cosine theta. So let me write this. The sine of 2 theta is equal to 2 sine theta cosine theta. That's the identity we're going to use. So ultimately, I now have r, the range, is equal to v0 squared sine of 2 theta over g, which I've written below your field of view. Okay, so there's the identity I found. Like I said, notice I was able to reason from physics grounds that it couldn't be the sine, so I was pretty confident it was the sine of 2 theta instead of the cosine of 2 theta, and that is actually a formula. Okay. Obviously, if the angle was 0, the sine of 0 is 0, so you get 0 range, and that's because we threw it from 0 height, so it would literally just hit the ground immediately. So, but if we threw it up, say straight up, then again you would have 90 degrees, but 2 times 90 is 180, and of course the sine of 180, which is pi, you can see is 0. So that would get 0 range as well. But that's what you expect. If you threw the ball straight up, you don't expect it to go horizontal at all. So that's a confirmation of the symbol working. What actually would give us the largest range? In other words, what is R max? And I'm specifically asking for the angle, so you could think about finding the extrema, if you will. And what would be the extrema or the maxima or minima of this range? If you actually made a plot of it, it might help you too. Notice theta only really runs from 0 to 90. It doesn't make any sense to do anything bigger than that. So if I actually made a graph of R versus theta, obviously when theta, well, I won't say it that way. When theta equals 0, I get 0. Notice the sine of 2 theta is basically the same thing as theta, but it all happens, or same as sine of theta, but it all happens within the first pi degrees. So basically I'm taking this entire graph and compressing it to half the size. So what that's going to be is I'm going to go from, let's say this is pi over, let's say this is just plain pi. And of course, it doesn't mean anything to have an angle of pi, but it does mean something to have an angle of pi over 2. But normally this graph would be this, and then just as far away would be it coming back to a 0. I got to fit all that into the same graph. So now what you see is it's going to go up, reach its maximum right here, cross here, reach its minimum, and then come back here. But again, these are not real angles. Okay, because theta greater than 9 over 90 or greater than 90 degrees, you might as well just say it's less than 90 degrees, but you were throwing it the other direction, right? So if this is pi over 2 and this splits it in between, what angle is this?
We can't see anything.
Oh God, thank you for telling me. Jesus. Okay, so what I just did was I took that whole sine graph, which would normally be this shape, and it would go over a distance of 2 pi. Since I had the sine of 2 theta, I've got to fit all that in half as much space. So I've got to fit the whole 0 to 1 to 0 to -1 to 0. Instead of fitting that in 2 pi, I've got to fit it in pi. So I just forced myself to do it this way. And then I realized that, of course, pi over 2 is the biggest the angle could be for a projectile problem, because it's stupid to consider any bigger angles, because, like I said, that's smaller than 90, just you're throwing it the opposite direction. Okay, so can you tell in this real angle range, 0 to pi over 2, what angle is that gives it the max distance? This one's pi over 2. What would this one be?
Pi over 4.
Pi over 4, exactly. And do you remember what that is in degrees? It's 45 degrees. So like you've heard in school before, or in baseball practice or softball practice or anything else, if you want to maximize the distance you throw and you're ignoring air resistance, the best angle is to throw it at 45, because you're basically, the bigger the horizontal velocity is, the farther it can go left and right in a given unit of time. But the bigger the vertical component of velocity is, the longer it can stay aloft. So if you balance those two and make the two components equal, you're probably getting the best case scenario. Obviously, balancing the two means using the angle 45 degrees, because then the horizontal and the vertical components are equal. And physically, that would say 45 degrees. So you see that the equation bears that out, that the range is V0 squared sine 2 theta. And of course, when theta equals 40 degrees, you get the maximum distance you can throw it, which is V0 squared over G. So we've gotten yet another equation, another result. Now all we really need is H max and V max. Let me, it's 10:46 now. That's not very late, but I'm going to go ahead and give you your 10-minute break now, mainly because I'm out of coffee and my breath's dry. I mean, my mouth's dry. So I need the coffee to loosen me up a little bit. So let's go ahead and be back at 10:56. And you can still ask me questions. I'm just going to walk to the next room and get my coffee. But you can also go get a drink or hit the head or whatever.
Can you hold the paper closer? There's a few things I can't read.
You broke up towards the end, so I didn't hear exactly what you said.
Can you hold the paper closer to the screen? There's a few things I can't see.
Yes. Yeah, absolutely.
Okay.
You need to see the top more or the bottom more? So there's
The bottom more. The bottom.
Okay.
Keep going. Yeah. Okay.
You can see all I wrote over to the left was T max, range, R.
Actually, I'm actually having issues reading. It looks red to me. It's the 1, 2, 3.
That pinkish color?
Yeah, I'm having a real hard time seeing that.
I'll try not to use that except for little arrows or something.
Okay.
Can you read it now? I mean, it's out of focus now because I got it so close. But
Yeah,
let me
actually,
refocus and then I'll scroll over it. See.
That's actually better, yeah.
There you go. So I was showing a way I could get T max. I could first find out what T max is by finding the final velocity in the y direction being equal to 0, which is what I'm saying there. And then that would actually give me what T max is, which I later went back and actually did. And I got V0 sine theta over G.
Okay, I got it. Thank you.
Okay. Remember the rule of thumb, like if you want a quick answer to projectile motion problems and you're using meters, just remember our G is about 10. So call it 10 and you can quickly estimate G rather quickly. And calling G 10, then that example I worked earlier, which was 58.8 meters per second in the vertical direction. Well, if I'm going to pretend G is 10, then that'll just be 60. So you can see it's going to lose 10 meters per second every second. So it'll go 60, 50, 60 is at 0 seconds, 50 at 1, 40 at 2, 30 at 3, 20 at 1, 2. Yeah, I started counting backwards. Sorry about that. 50 at 1, 40 at 2, 30 at 3, 20 at 4, 10 at 5, and then finally you'd see 0 at 6 seconds. And then, of course, it'd take just as many seconds to fall back down, and you get that same 12 seconds that we had earlier. If I wanted to quickly figure out something like the range, well, if I did use 60 meters per second and I threw it at an angle of 45 degrees, then you see the sine of 2 times 45 is a sine of 90, so that's just 1. So I'm back to this formula. So if I threw it at 60 meters per second, that would be 60 squared over 10. Of course, 60 squared is 3,600. And then divide that by 10, that's 360. So 360 meters is what you'd expect someone to be able to throw if they could throw at 60 meters per second, which, by the way, is friggin' fast. Okay. That's more like a tennis serve. That's not a baseball pitch. I don't think we have anybody that's ever thrown more than 112 miles per hour. As far as softball, I mean, as far as tennis goes, I think we've had the fastest serve is 165 miles per hour. So that's on the order of, I can't remember how many kilometers per second or meters per second, but anyways, you have to work that out. Were you able to get everything you needed to see there?
Yes, thank you.
You're welcome. Anybody else while we're waiting? Remember to write these boxed off equations somewhere so you can use them over and over when you're doing just straight projectile motion problems. You don't have to reinvent the wheel every time. I would suggest you go through the process of deriving these equations once, twice, 3 times, however many times it takes for you to be able to do it on your own, because by then you'll remember it. As you can see, the only thing you really need to have memorized to do this so far is just this one trig identity, sine of 2 theta equals 2 sine theta cosine theta. And we're almost done. All we have to do is V final and H max now. Unless you got a real commotion going on in your background, why don't you leave, if you're one of those people that don't have a lot of commotion in your background or any commotion in your background, I would ask that you leave your microphone open, unless you just, want the privacy. That's fine. I understand that. But if I had one person that did that and that they would instinctively let me know when I'm being an idiot and writing below the screen, I don't mind at all you telling me, Mr. Younger, you're gone off the screen again. Because I've moved this closer so that y'all can see better, but now my field of writing is a lot smaller. So I now, even more often than normal, go off the screen. All right, got 4 more minutes. Oh, by the way, I mentioned a great book to you. I found that it's at Project Gutenberg, so you can get it for free. It was actually the first science related book that Michael Faraday ever read. And it was impressive because, this is the late 1800s, early 1900s, but it was already out in the late 1800s. So we're talking 1850s, and even earlier was when she was writing it. The book is Conversations. I'm going to write it in the chat notes. Conversations on Chemistry, and it's by Jane Marcet. Okay, so Conversations on Chemistry by Jane Marcet. It's a free book. It's neat. It teaches you a lot of cool stuff about chemistry, and the fact that it was written by a woman in the 1800s is and was a fairly popular science book is impressive. And it's easy reading, and you can probably all, even with the limited science that you may or may not have had, you can probably tell what they were wrong about, because that in that case they think heat is caloric, and caloric's like a fluid that goes from one object to another but has very distinct rules. So that stuff you can tell is sort of going to turn out not to be the right answer, but it still behaves the same way. So it doesn't matter that it was right or wrong as long as they get the right results. So they actually teach a lot of the cool phenomena, like, why flannel is good to wear, say, in the winter, and why dark colors are better than light colors in some situations, and why other situations light colors are better for clothing. So it's got a lot of little practical stuff. Plus it tells some really cool experiments that were done. I'm reading a bunch of different books right now. I'm reading that. I'm reading Lines of Force, Faraday's Lines of Force by Maxwell. And I'm actually reading Faraday's book on his lines of force. I'm reading Heavisides electrodynamics, which is basically him taking Maxwell's equations and making them simple, which is still not simple, of course, but compared to what Maxwell taught, it's a lot simpler. All of those are free. I'm also reading 2 biographies of Maxwell and Faraday and Heaviside, and those, of course, are not free. They were fairly recently written, but are good. All right, got about 1 more minute. Still no more questions?
Hi, Layla. Oops, still on mute.
All right, time's up now, so let's go ahead and get back started. Anyone have any questions before we move on? I just want to let everybody know, I just wrote in the chat Conversations on Chemistry by Jane Marcette. That was, like I said, a free book that you guys could download if you wanted. It runs on the Kindle app. You could get it in PDF form and it'll read it. You can read it in anything that opens PDFs for you. You can just use the link in your browser so you can read it on the web if you want. But it's a really good book written by a female, not a scientist really. She was the wife of a scientist, but she was very, very bright and very well exposed to science. Her husband was a medical doctor, and she got to see some of the world's greatest scientists because they were both intellectuals and curious about nature. But she's explaining basically what we've learned about chemistry and how that can help us function in everyday life. I think she might have, I mean, she meant it obviously for everyone, but in this case, she's sort of addressing it like these are some things that women might want to know. So I like it. It's really great. Highly recommended. The name of it's there in the chat, so check it out. Let's go on. What I said we would try to solve for is the range. I didn't even mention the max range, but I'll work that out. By the way, you could also get that max range by taking this and take the derivative with respect to theta, set it equal to 0, and then you'll actually find a theta that gives r being the max, and of course you'll find the exact same answer we got before, namely theta must be equal to 45 degrees or pi over 4. So that's another way you can come up with that formula. The only things I have left are the final velocity and the height that it reaches at its highest point. So the H max I'm going to attack now. There's a couple ways you can look at this physically. You can realize that H max occurs when the vertical velocity becomes 0. So if I take this crazy equation that I made here, and remember I took a derivative of it to get the velocity. If I set the vertical component of velocity equal to 0, then I will get the time at which H max has occurred. Well, I already did that. That was called T max, and I found it to be V0, or excuse me, I found it to be V0 sine theta over G. So now that I know what time the y component of velocity is 0, I can now see what is the y component at that time. So really all I have to do is set this or find out what this equals when t equals v0 sine theta over g. So that's how I'm going to go about finding the H max. Another way you could do it, of course, is set the y component of position, take the derivative of it with respect to time, and see when that's a maximum. So when you find the y position as a maximum, that'll be a very specific time. Guess what? It's going to turn out to be T max. And this, guess what? When you plug that back in, you'll get the H max formula. So there's 2 different ways that you can do it. You can probably find a bunch more as well. So what I'm going to do is I'm going to say, let's find H max. V final sub y is equal to 0. That turned out, remember we said 0 is equal to V0 T, or no, just plain V0 sine theta, that's the y component, minus gt, and we got t is equal to v0 sine theta over g, which is at t max. So that is actually t max. But now all I have to do is plug it in this particular expression, because remember, this whole thing is made from kinematics, so I can just plug it in there. Or I can just take the kinematic equation and say, let's make it for y instead of x. I'll say y is equal to y0 plus 1/2 a sub y t squared plus v0 sub y t. Well, when I plug all that junk in, I'm going to say h max is equal to the final position. The initial position, of course, is 0. The acceleration in the y direction is negative g, so it'll be minus 1/2 g. The time we found was v0 sine theta over g, but that's going to be squared because it's time squared, plus, now I'm going to say v0, and now I'm going to plug in that time again, v0 sine theta over g, and then it was v0 times sine theta, so I'll put a sine theta there as well. So that's v0 sine theta, and this is t. So we basically have everything we need. If I work this out, I think you can see that h max is going to be equal to, notice the g's cancel out top and bottom here, so this g is going to disappear with this g, and I'm going to get negative v0 squared sine squared theta over 2 plus, oh, this was actually 2g. Remember, this was squared, so only one of those will cancel out. So it's v0 squared sine squared theta over 2g. This one, on the other hand, is going to be v0 squared sine squared theta over g. So you can see this is half as big as that. So basically I've got, if I factored out everything but the 2's, I would have 1 minus 1/2, or negative 1/2 plus 1. So obviously that's just 1/2. So I'm going to say it's v0 squared sine squared theta over 2g is h max. Okay, I'll box it off with a pretty color too. So that's the max height. Okay, so somewhere along the path, especially if you're throwing from ground height and it's landing at ground height, you take the midpoint of that path, and that will be when the projectile is at its highest. At that point, its height will be v0 squared sine squared theta over g. Let's check the units. v0 squared units would be meters squared per second squared. G in the bottom is meters per second squared. So it ends up becoming meters squared per second squared times second squared per meter. So obviously you're just left with 1 meter on top, and that's exactly what we want. So the units did work out. So now I've got yet another variable we've correctly solved for. Now all I need is the final velocity. Well, for final velocity, what we know is v final is going to be v final in the x direction, I hat, plus v final in the y direction, j hat. But since we assumed there was no air resistance, the x velocity was a constant. So we already know the x component of the final velocity. It's just v0 cosine theta. The y component, however, well, that's going to be from our, if you want to use the non-vector equation, we could use, for instance, we could use v squared is equal to v0 squared plus 2ay minus y0. And again, since I made that y, I'm going to put a little subscript y on everything, and we'll know what it is. We could find out what the final velocity is just by figuring out what the initial and final heights were. But those are both the same, so that's not going to help us, right? V and V final are both the same height if we're talking about if we're talking about when it hits the ground. So that's not going to help us. But we could also use the equation that says V is equal to V0 plus AT. And again, since we're using it in the y direction, we might need a subscript y. So now I can see that clearly the final velocity is going to be the initial velocity minus gt. So I'm going to say V0 sine theta, that's the y component of velocity initially, minus gt j hat. But that's the velocity at any point in time. We want the velocity at the end of time, which for our example was 12 seconds, for instance. But in here, it's the time t max, which is 2v0, or it's t total, excuse me, 2v0 sine theta over g. So I'm going to plug that in, and I'll find that v final sub y is equal to v0 sine theta minus g times 2v0 sine theta over g. This time the g's really do completely cancel out because the time wasn't squared, and I got v0 sine theta minus 2v0 sine theta. So v final is in fact going to be negative v0 sine theta. So that's one of those beautiful symmetry things. Because it took off from the same height that it landed, the y component of velocity is basically when it reaches zero height. So it'll have the same velocity downward as it had upward. So the final velocity, v final, is actually equal to v0 sine theta, or excuse me, v0 cosine theta I hat minus v0 sine theta j hat, which literally means it has the same magnitude of the initial velocity. So v final magnitude is just equal to v initial, but the y component just reverses. So you can write this as one result, and you can write this as another result. But that's what happens when you throw a projectile up. Just like if you shoot a bullet in the air, if you shoot it straight up, it's not very safe. You know, if you watch, dang it, I can't remember the name of the movie, with King of Queens in it and Adam Sandler and all of them, and they're out celebrating the coach's death or something, or one of their friends' death or something. And basically one of the things they do is they shoot an arrow straight up in the air, and they see who can stay there long enough just in case it's going to hit them. Yeah, so that's the danger. Grown-ups, thank you. I could think of the word grown, but I wasn't coming up with ups. So yeah, in the movie Grown-ups, that's why it's not wise to shoot things straight up in the air, even with air resistance. Then it's like me telling you, hey, would you mind if I shoot you in the chest with this rifle? Only I'm going to give you, don't worry, I'm going to give you an air-filled bulletproof vest. It's made out of garbage bags, right? It's a garbage bag filled with air, and it's going to block it, the bullet from hurting it. That's literally what's going on if you throw a projectile or shoot a bullet straight up in the air. You're using the air resistance of it going up, which slows it down, slows it down, slows it down. And then when it comes back down, it slows down, slows down, slows down as well, even though it's still speeding up. So it will have a decreased velocity by a lot, but I don't want to wear a air-filled garbage bag bulletproof vest. So specifically because it's not bulletproof, it's not even, maybe not even bullet retardant. So anyways, that's why it's not wise to do that. Don't do that. Don't be that guy. Okay. Anybody have any questions on that? So notice I worked out everything in symbols, and you might think, well, this is stupid. He hasn't done any problems. Well, what I've done here is an infinity of examples. By working this out in symbols, I have the answer to not one problem, but an infinity of problems. I have an answer for every V0 and theta that's reasonable. So any angle between 0 and 90 degrees, and any velocity that you can throw it at, where air resistance is not going to become a problem. I've gotten all those solved by using these equations. Okay. Remember, if these equations are memorized by you, you can use them. Or if they're actually numbered in your textbook, then you can use them and actually write them down. But if they're not numbered in your textbook, you're not allowed to write them down. If I remember correctly, they did not number these in your textbook. So these are not ones that you're allowed to have on your cheat sheet during the midterm. But like I said, if you go through this derivation yourself, I think you will remember them well enough where you won't need to have them on your cheat sheet. You'll just know them. So any questions on that? So let's actually work a physical problem. Let's work a problem where I launch a projectile off of a cliff and I find out, how far, or let's think of it this way. Let's say a car is driving quite fast towards a cliff. This is a Thelma and Louise moment. Okay. So we're going to say a car is moving at 60 miles per hour headed towards a level cliff. And the cliff is, let's say, 1,400 feet high. Okay. Thelma and Louise are driving at 60 miles per hour towards a cliff that's horizontal. They're going to launch off this. The height, h, is 1,400 feet. Again, notice I'm using units that you're more familiar with instead of the units that physicists like. So we got to do some conversion stuff. And I'd like to know how far downfield it's going to land. So it's going to go like this. I would also like to know its final velocity. And I'd like to know the time required. So how long are they scared poopless? Because as soon as they leave this cliff, it's going to be really scary, right? So how long do they suffer that fear of, we might call it the yell time. How long can they yell? Okay, so first off, 60 miles per hour. I've told you how to do this conversion. So I'm not even going to do the conversion. I'm just going to give you the right answer, and we're going to deal with that. So let me see. If you wanted to convert that to meters per second, you could, of course, convert the miles to feet, and then feet to inches, and then inches to centimeters, and then centimeters to meters. And then you can convert the hours to minutes, and then minutes to seconds, and you'd have meters per second. But Mr. Younger has an HP calculator. So he's going to just put in 60 mph and then write 0 meters per second under it and tell it to add. And it's going to tell him it's 26. And I'm going to pretend like I got 4 sig figs, 26.82 meters per second. Similarly, I'm going to say 1,400 feet. Now, in this case, I would actually want to convert it from feet to inches, from inches to centimeters, and then from centimeters to meters. And that's all well and good. I can do that. But in my calculator, all I'm going to do is put in 1,400 feet, and I'm going to add to it 0 meters. And it's going to spit the answer out as 426.72 meters. 426.72 meters. Okay. So I'll pretend this number has 4 sig figs and this number has, which is really an unreasonable amount of numbers, but this one has 5. Okay. Now, with that in mind, let's figure out our answer. So first off, what I want to know is how far is it going to go? Well, I know it's going to travel horizontally from here to here at a constant speed of 26.82 meters per second, right? It's just a matter of how long is it going to take to fall from here to here. And in fact, this is just like those 2 balls that I showed you on page 63. The one shot off horizontally is like the car, and the one drop from the same height is like the yellow ball. And what you're seeing here is if I figure out how long it takes to fall from a height of 426.72 meters and land, then I know how long it's in flight. So I'm first going to solve for time. So time equals question mark. The way I'm going to go about doing that is I'm going to use the x is equal to 1/2 at squared plus v0t plus x0, like that. Of course, I'm actually tweaking it for the y direction, and that's fine. And it looks like a horrible thing because you're looking and thinking quadratic formula, right? But no, you're not quadratic formula because it's going to turn out that one of these x's is 0. So it actually, it might turn out, but we'll see. Oh yeah, it doesn't, because the initial velocity in the y direction is 0. So for this one, what I'll have is I want y equal to 0 as the final result. So I'll say y equals 0 is equal to -1/2 gt squared. The initial velocity, of course, is 0, and that's because it's in the y direction. This v is horizontal, is why that y component of velocity is 0. So I don't have that term at all, but I do have that the final height or the initial height was 426.72 meters. Okay. So what I've done is I've made the coordinate system be such that y is here and x is here. In other words, the origin is down here, because I'm asking for when it hits the ground, and I called that y equals 0. So that must be the origins lined up at ground height. So now I can just figure out that, in fact, 1/2 gt squared is equal to 426.72 meters, or t is equal to 2 times 426.72 meters over g, which is 9.80 meters per second. And that's actually t squared. So t is going to be equal to the square root of all that junk. Let me compute that. So 2 times 426.72 and divided by 9.8. That gives me 87.0857. Carrying way more digits than necessary. The units turn out to be, notice the meter up here cancels out with the meter down here, and I end up getting seconds squared. And when you take the square root of second squared, you're just going to get seconds, which is what we expect. So now I'm going to take the square root of that, and I get 9.331 or 20. 9.33. Actually, I'll go ahead and write down more digits. 1973 seconds. Now, what I had was I had 426.72, and then I took that number and divided it by 3 sig figs. So that left me with only 3 sig figs. So really, I have to round this to 9.33 seconds. In other words, all these digits are extraneous. So I now know that they were suffering for 9.33 seconds as they're flying off the cliff. They're going, ah! So it'd be hard to exhale for 9 seconds straight. A little difficult anyways. So, and that's a bummer, because I really hate how long that is, because I've always been a little apprehensive about flying. And if you're thinking about flying an aircraft, now all of a sudden I know there's a long time period that you know something bad's going to happen. Ooh, I hate that. Ooh. Okay, so now we've gotten that one. Let's find out how far it goes horizontally. Well, we're going to know how far it landed downrange, because it's actually moving at a constant 26.82 meters per second to the right. So I already know that basically it's going to cover 26.82 meters per second. And I know generally it's going to take around 9 seconds to get there. So I'd expect this is going to be, if I made it 10, it'd be 268 meters, but then I got to subtract 26 from that. So 268 would become 242 meters roughly, and then a little bit more. So maybe I say 245 meters it might be the right answer. But let's work it out. We know that x is equal to v0 x in the times time. So because of that, I want to say 26.82 meters per second times 9.33 seconds. And I'll carry extra digits on this one. I'll underline the extra digits so I can keep track of it. And that's seconds. So I see times 26.82. That's 4 sig figs times 3 sig figs. So I really got to round this. I said the answer is going to be about 245. The answer comes out to be 250.28. 284. And that's meters. Okay, meters per second times seconds. So what I'm going to report is X is actually equal to 250 meters. So my approximation was pretty good as well. And that's again what John Archibald Wheeler was saying when he tells you never solve a physics problem you haven't already solved. He wants you to estimate or use some physical reasoning when you start a problem to get an idea of what the answer should be. And then each time you're solving a physics problem, you're not only learning how to solve a physics problem, you're doing an experiment. You're testing your understanding of physics and your understanding of the equations relating to matters to quantities in physics. And if you find out your approximation was way off the mark, you need to figure out what was wrong with your understanding of physics. In this case, we were pretty close, so I'm happy with that. So now I've gotten that and I've gotten the time. Now all I need is the final velocity. Well, basically the horizontal component of velocity is going to stay the same. So that's going to be 26.82 no matter what. But what we're doing is we're actually allowing gravity to act on the velocity vertically for 9.33 seconds. I still can't believe how long that is. But I guess 1,400 feet is really, really, really high. More than half a mile. So yeah, I guess that's reasonable. So 9.33 seconds times 9.8 is really what the velocity is going to be. So we can roughly say it's around 98 meters per second vertically. What I'm going to do, that was a rough estimate of what the answer is. What I'm going to do is say V y is equal to V0y plus AT. In this case, the AT is negative G. So I'm going to get Vy is equal to the initial velocity is 0 minus 9.80 meters per second every second times 9.33 seconds. Now, really, I'm again using those extra digits. I'm not really using the 9.33. So I wanted to point that out to you. So V final Y is actually going to be equal to 9.80 times 9.331973. Again, I'm doing 3 sig figs times 3 sig figs, so I should get 3 sig figs. This answer turned out up here to be 91.4533. Meters per second. Notice meters per second multiplied by seconds just gets rid of one of those, and you're just left with meters per second. So I'm going to round this appropriately to 91.5 meters per second. And notice it actually comes out negative because the acceleration was in the negative direction. So negative 91.5 meters per second. I'll say the final velocity is in fact 26.82 meters per second in the I-hat direction minus 91.5 meters per second in the J-hat direction. Again, you can actually use that to figure out the magnitude and direction. This is a little under a third of the vertical. So that's what the actual velocity should look like, is that. This being the final velocity at that angle. So that's V final. This is 26.82 meters per second. And this is 91.5 meters per second, which really I would use 91.453 or at least 0.45. And I want to know this angle phi. So the angle phi is equal to the tangent inverse of 91.5 over 26.82. Again, like I said, I'm using more digits than I'm really representing there. So I'm going to say $91.45334 divided by 26.82. I'll take the inverse tangent of that. and I get 73.655 degrees. Obviously, that's 3 sig figs and 4 sig figs. So really, these are extraneous digits right there. The magnitude, of course, VF, is equal to the square root of 26.82 meters per second squared plus 91.5. Again, I'm still going to use more digits than just the 91.5. It's just easier to write the smaller quantity. So I'm going to say 26.82 squared plus 91.4533354 squared. And now I'm going to take the square root of that, and I get 95.3049 meters per second. So I'll really, again, realizing that that is one decimal place, 91.5 squared is really 8,370. So I really only have a tenth, down to a tenth when I square 91.5, because 91.5 times 91.5 is 3 sig figs times 3 sig figs. You're only allowed to have 3 sig figs. Well, that's 8,372.25. Well, 3 sig figs only gets you to the tens place, so I really shouldn't be carrying this number beyond the tens place. So technically, I should call this 100 meters per second, but that's a really ugly rounding issue. So I don't like it. I'm going to go ahead and carry it to an extra digit, and I'm going to say the velocity is 95.3. I'll underline that, meters per second. And that's measured downward from the positive x-axis. So that's a negative 73.7 degrees. So that's another answer for it. Notice we could have done that same thing with the projectile earlier, but I think you can tell by the symmetry of it, the x component is going to be the same as the initial x component. The y component is going to be the same as the initial y component, except it's downward. So instead of positive 60, we can see it's going to be V0 is equal to that, and VF has an angle of theta equals negative 60 degrees. So that's really the only difference, because it's now 26.82, the same thing it was horizontally before, but it was whatever I found the vertical component of velocity to be, V0 sine theta. That's was upward. Now it's downward. So we know the angle is just going to switch from theta to negative theta. So V final is just equal to V initial and at negative theta degrees. So that's another way we can write it in addition to that. So I can just write V final is equal to same magnitude, but it's now at negative theta instead of positive theta. With this one, we can't do that symmetry thing because it was launched from a different height than it landed. But notice it did land with a velocity that is, that's pretty darn steep, 73 degrees. That's reminiscent of the fact that it really is a high mark. So the fact that it had all that time, 9.33 seconds, meaning the car kept going down like this. And remember, the engine of the car, of course, is the heavier part. So the center of mass, which is the thing that's going to try to accelerate downward, is going to accelerate or is going to be closer to the engine. In fact, it'd probably be about lined up with the back of the engine. And then the whole car is going to tend to rotate about that. So it might even land upside down or something like that. But that's something we'll talk about when we talk about rigid bodies. Any questions on this problem? So I've found it both ways, but really, actually, I should even put this as underlined because really the magnitude is only to the nearest tens place. And that's 95. So I should call this a flat 100 meters per second, but I don't like that. I want to include a couple extra digits. So it's 95.3 is what we'll go with. Any questions on that? Okay. Another neat problem is one that we do all the time in physics, and I call it the shoot the Barney demonstration. So I used to, when I was at Chapel Hill, and also when I was at my previous school, I often would go out and do fun physics demos and stuff like that. You know, lay on a bed of nails and let my rather large muscular brother crush a cinder block on my chest while I'm laying on the bed of nails, take liquid nitrogen and bust things with it and crumble flowers. And I could even make a blowtorch out of it, which is kind of neat. A little dangerous though. If you have any kind of fillings, your tooth will explode, and that's a horribly painful situation. Stuff like that. Flamethrower I'd actually make out of cornstarch. But one of the things we did was a shoot Barney demonstration where basically, let me show you in my face for this one. So basically what we had was a gun, a little projectile like the one we use in our lab for projectile motion. It just shoots a ball out, and you can set it at any angle you want. We had a laser pointer on it, so the laser pointer actually aimed exactly where you were aiming at. And then off in the distance, we had a pole holding a Barney doll that had Velcro on its front, and the ball had Velcro around it, you know, male Velcro on the ball and female Velcro, say, on Barney. And we had a timer set up such that the instant the ball came out of the barrel of the gun, the timer saw that and let go of or told the magnet to let go of Barney, because there was an electromagnet there. So it would pull the electromagnet away from Barney, and Barney would fall at the same instant, like zero delay. It's probably on the order of a millisecond delay. But either way, the instant you fire, Barney's going to drop. This was an old problem that we used to solve in physics, where there's a monkey in a tree and you're trying to shoot him, let's say, with a dart gun. The instant the dart gun noise reports to the monkey, which you assume is way faster than the dart itself, the monkey's going to get scared and let go of the tree and fall down. So do you aim above the monkey while it's in the tree? Do you aim directly at the monkey while it's in the tree? Or do you aim below the monkey while it's in the tree to compensate for the monkey dropping down? Does anybody have an answer on that? What do you think the right answer might be? Always have a guess, no matter if you're sharing it with me or not. Always have a guess. Okay. What I'll do is I'll work it out. I'll have some numbers, but I'm going to use it basically symbols so you can see what all works out. So what I'm going to do is I'm going to say, okay, we have a projectile being fired from, say, the origin. This is the x-axis. This is the y-axis. And probably I want to see the document, I'm assuming, instead of just the top of my head. So Mr. Younger has got a Mensa moment there. Mr. Younger was so smart, he figured it out on his own. So let's say over here, some distance, let's say capital X is the spot directly under Barney. Okay. And let's say capital H is the height of Barney. And in fact, Barney is actually going to be like this, sitting here, okay? We're going to fire the projectile at some angle, and this is the angle, of course, to actually Barney, okay? But we're going to fire the projectile at some angle. I'm going to say V0 is equal to 3.00 meters per second. And I'm going to say that X is, let's say, 3 meters. And I've got plenty of height here. So like maybe this is sitting up on top of a table that's 9 feet high or something. So even if it takes so long to hit it that it's going to hit it way down here, I've got plenty of height to pretend I'm working with. I'm going to say H is in fact 2 meters. And I'm going to assume all those are 3 sig figs. So this is actually 3.00 meters. And this is 2.00 meters. Okay. Now, what I want is the position of the projectile to equal the position of Barney when they're both at X. Okay, so I can set up an equation for the projectile. So I'll say x projectile is equal to v0 t times cosine theta. Okay, I haven't given you a theta yet. Does anybody want to take a guess at what theta might be? And actually, let me change the 3 number and the 4 number. I just thought of a better way that this will probably be more instructional. Instead of using 3 meters and 4 meters, I'm going to use something else. Or 3 meters and 2 meters. I'm going to use 4 meters instead. So what I'm going to say is the height is actually 4.00 meters. And that means I didn't need to erase the x. So another Mensa moment from your favorite physics instructor. So it's 3 meters over and 4 meters up. So does anybody, if you know 4 meters up and 3 meters to the right, you know that that's our 3, 4, 5 triangle. And I think you know that the angle for our 3, 4, 5 triangle, one of them's like 33 or something like that. And the other one is like 53.13. Yeah, it's 36 point something and 53.13. So this angle right here, which might be entirely different, by the way, that angle phi is 53.13 degrees. That's just our famous 3, 4, 5 triangle. So you might want to commit that to memory anyways. It comes in handy. 4, 3, 5, 53.13. And now I subtract from that 90, or subtract it from 90, and I get 36.87. So the other one would be 36.87. So that's the angle up there as well. So do you think I need to shoot at a higher angle than 53.13 or at a lower angle than 53.13? Remember, it's usually more valuable when your hypothesis is wrong, so it's not a big deal if you're wrong. Okay, so we're going to go with the hypothesis that clearly everybody's given me, which is no answer whatsoever. Okay, I'm going to tell you I think the answer is 53.13 degrees, because that picture on page 63 showed me that horizontal motion and vertical motions do not interact. So if I aim this projectile directly at Barney and then I fire at the same time as Barney is dropped, then gravity is going to act on the projectile the exact same amount that it's going to act on the bear. So if I shoot it really fast, I'll hit Barney right below where it was dropped. If I shoot it really slow, I'll hit Barney considerably lower. If I shoot it really, really slow, maybe I'll hit it just before it hits the ground. Either way, that all works out. So I'm making the hypothesis that the angle is 53.53 degrees. I know the x position of the projectile is going to be v0 times t cosine theta. I know v0, of course, is 3 meters per second, and I know theta is 53.13 because that's what I'm going to try to aim it at, but we're trying to solve for theta to actually find what it is. I'm hypothesizing the theta will turn out to be 53.13. The y position of on the other hand, of the projectile is just going to be v0 times, notice it's going to try to move at a constant velocity upward. That constant velocity upward would be v0 sine theta. So I'm going to say it's v0t times the sine of theta minus 1/2 gt squared. That's my y position of the projectile at any point in time. And now I can also say the x position of the Barney as a function of time, that's just going to be plain capital X, right? But the y position of Barney, that's going to be, it has no initial velocity, so it's actually going to be having an initial height of h, and its final, it's going to decrease that height by an amount negative 1/2 gt squared. Okay. So I've worked out an equation for y as a function of time for Barney. I've worked out an equation for x as a function of time for Barney. It's always capital X. I know h, I know g, I know x, excuse me. I know v0. All I need to know is, of course, theta. So I've got all these expressions, and I know which variables I know. What I'm going to do is I'm going to find the time it takes for my projectile to reach this position. So t projectile at x. So I'm going to find the time at which the projectile is at the x coordinate. Well, that happens to be x equals v0 t cosine theta. So t at x is equal to x over v0 cosine theta. So that's the time, no matter what angle I shoot it at, assuming it's high enough to where it's not going to hit the ground before it gets over to x, this projectile will be directly over the spot x at a time x over v0 cosine theta. That's pretty straightforward, right? You knew the velocity's just a constant v0 cosine theta. So if you divide the position by the time by the velocity, you get the time. But now what I want to do is I want to take that time and I'm going to force y projectile to equal y bare. So y projectile equals y bare. That's going to give me v0t sine theta minus 1/2 gt squared is equal to h minus 1/2 gt squared. So you can see already that the 1/2 gt squared on both sides are canceling out. That really is telling you exactly what I said about the two balls on page 63. The amount of change in height is the same whether the ball was dropped or moved or shot up at some speed, right? Because they both were corrected by that factor. So now all I have to do is substitute my t in here, and I'll say v0 times x over v0 cosine theta times sine theta is equal to h. So you can see that the v0s cancel out. This came from this equation. So this v0 cancels out with this v0. And sine theta over cosine theta is just tangent theta. So I'm going to say tangent theta is equal to h over x. But h over x, of course, is 4 over 3. So theta has to be 53.13 degrees as hypothesized. So that's just kind of a neat problem. I was able to work it out in terms of symbols, but I could give you the real deal with regards to the answer. So let's actually work out the numbers and see what it would be. Well, t is equal to x over v0 cosine theta. Well, we figured out that theta is going to be 53.13, x is going to be 3.00 meters, v0 is going to be 3.00 meters per second, or excuse me, v0, not v3. And that's going to be times the cosine of 53.13 degrees. Of course, you can look at this and realize that the cosine of 53.13 is 3/5 or 0.6. So it's 3 divided by 3 divided by 0.6. So basically, it's just 1 divided by 0.6, which is 1 divided by 6 over 10, or 10 divided by 6. And 10 divided by 6, of course, is not that easy, but 1/6 is 16.66%. So this should be 1.66 seconds. I'm pretty sure that's the way it works out. Let me do the math. 1 divided by 0.6 is 1.66 seconds. And technically I should round that to 1.67, but that's neither here nor there. So I've now got the time. So is the projectile actually at x equals 3 meters? Well, the x position of the projectile, xp, at 1.6, let's put an extra digit in there. So I'll say 1.667 seconds is equal to V0, which is 3.00 meters per second, times 1.667 seconds times the cosine of 53.13 degrees. Again, this is 0.6. This is 3. So 3 times 0.6 would be 1.8, and then times 1.66. I think you can see if you do this with your calculator, 3 times, this is 1 2/3. That's the easiest way. So 3 times 1 is going to give me 3, but 3 times 2/3 is going to give me 2. So it's 3 plus 2 be 5. And then I divide, multiply that by 6/10. So that would be 6 times 5 over 10, which is 30 over 10. That's 3.00 meters. So it is at the right distance horizontally at that time. Now let's see if it's at the right height. In other words, what's the height of the projectile and what's the height of Barney? Well, the height of the projectile would be V0, which is 3.00 meters per second. I'm going back to this original equation that I did here, times 1.667 seconds, times, in this case, it'll be sine of 53.13 degrees. And of course, sine, you know, from this is 4/5, so that's 0.8, minus 1/2, 9.80 meters per second times 1.667 seconds squared. Okay, so this is 3 times 1 2/3. 3 times 1 2/3 is 5, like we found out before. And then 5 times 0.8 would be, 5 cancels out with a 10, leaves a 2 on the bottom. So 8 divided by 10 is 4. So this part right here is 4.00 meters. And then, which obviously is the height the ball was initially. And then 1/2 of 9.8 is 4.9. And then 4.9 times 1 is 4.9. And then 4.9 times 2/3 is 4.9 times 2/3. I could actually do this, but I'm suspecting that I will make some kind of careless mistake when I multiply 4.9 times 2/3. So that should be 3.267. So this should be 3.267 meters, roughly. Oh, it's supposed to be that times 2/3. Sorry, twice. Times 2 divided by 3. That should be 2.177. Sorry about that. So it's going to be 2.177 meters lower than 4. Well, this thing, the bear, is going to start off at 4, and it's going to subtract that exact same amount, 1/2, 9.8, 1.667. So it's also going to be 2.177 lower than 4. So that does, in fact, equal y of Barney. So we've now checked that the numbers work out as well for the physical problem, as well as just the straight symbols. Any questions on that? So that's a pretty robust problem, worked out in, you know, gory details, all the gory details. So I think that's a pretty good cut of projectile motion. If you want to study something else, you could also study the examples in the book. They did in example 310 work out the actual projectile motion stuff. So they got R is equal to V0 squared sine 2 theta over G, just like I did. They found that R max happened when theta equals 45 degrees. All sorts of stuff that I had as well, but you'll notice that was an example 310, so they didn't actually number the equations. That's why you're not allowed to put them on your equation sheet. But if you derive them and memorize them, you can use them all day long. I don't mind at all. You can also solve a problem like 312 where it gets a little more complicated. What are the possible angles at which you can fire something out of the front of a helicopter that has a height of 200 meters? If I want it to land, say, on the top of a volcano, like in example 312, that's just another problem where you're going to analyze the horizontal motion separate from the vertical motion and determine basically what parameters you need to. Usually it's the time to figure out what angle you have to fire it at to get it to hit the volcano at the right spot. You can see from the range equation, which was just for a projectile that starts at one height and lands at the same height, you can see that you actually, unless you're doing the very maximum distance that it can go, which is the R max, if you're doing any distance lower than that, then there's two trajectories because the way sine theta works. Remember, I did a graph of this. I'm going to put it over here real quick and show it to you. Put it back on my document cam. Remember, I did a graph of this max range or the range formula. So this is just this formula. Looks like this. You can tell, hey, if I want a distance of R max, that's only going to occur for pi over 4 or 45 degrees. But for every other angle that you want to do, or every other distance that you want to do, if you want the factor to say be 1/2, then you go across here and you see, oh, it's that angle and that angle. Well, this angle and this angle are the same size. In other words, the distance from the central peak is the same here as it is from the central peak to here. So if you found that this angle occurred at, let's say, 45 degrees, or that's not say 45, if you found this angle occurred at 20 degrees, then that is 25 degrees less than the peak. If I added 25 degrees to the peak, then I'd get 70 degrees. So both 20 and 70 work. In other words, the difference between 45 and the angle in absolute values are the same. So for every projectile you fire, as long as you're not going to the max height, you get one for an angle like that, and you get one for an angle like that, where this one corresponds to theta equals, let's say, phi, or let's say 45 degrees minus phi, and this angle right here corresponds to theta h equals 45 degrees plus phi. So every possible distance will be equidistant from 45 degrees for a given angle. So this angle, for instance, could be 10 smaller than 45. And then this angle, of course, would be 55. So this is 35 and 55. That's one candidate. You could also have a candidate of 30, which is 15 below 45. If you have a candidate of 15 below 45, then you must have a candidate of 15 above 45. So 60 and 30 should give you the exact same range. So again, as long as you're not shooting for the maximum distance, which is V0 squared sine 2 theta over, or excuse me, which is V0 squared over G, as long as you're not shooting for that particular distance, if you go anything shorter than that, then you have a high trajectory and a low trajectory. And you've probably seen this probably in basketball when people shoot free throws. Shaquille O'Neal was particularly bad at free throw shooting. He got better at one point, but he still sucked. But part of the reason is he's so darn tall, it was probably more natural for him to use the low trajectory. Well, the low trajectory is just riddled with all sorts of error because it could, if you're just off a little bit, it's going to hit the rim, which could cause it to bounce backwards, straight up, straight forward. A lot of those things, a lot of those different errors end up in it just bouncing around and not actually going in the hole. Whereas if you shoot the high trajectory, the ideal angle would be such that the center of the ball goes through the center of the rim, but the rim is actually twice the width of the ball. Because of that, you actually have quite a bit more error when you're coming from the high angle. So you can actually do a little this, and you've got a whole ball width to play with. So the high trajectory is always the better trajectory, unless you got someone trying to, of course, smack the ball out of the air. And as long as they do it before the peak, that's not goaltending. But once it reaches the peak and starts to fall down, they're not allowed to smack the ball away. But even that, catching the ball before the peak when you shoot a high trajectory, that's harder for a player to block than the low trajectory would be. So the high trajectory is essentially the best for all of them. Any questions on that? Okay. Well, I think that does a pretty good number of examples regarding projectile motion. These sections we're covering this chapter are all of them. I've done a projectile motion, a relative velocity problem before, but that was all one-dimensional. So let me work another problem related to relative velocity, and we'll go from there. And probably time will be up at that time, and then we'll take a break and go to the lab thereafter. So let's imagine this. Let's imagine we have a river running from east to west. So the river's running this way at 1.00 meters per second. That's the velocity of the river as seen by Earth. And since that's a negative direction, I'm going to call it negative I hat. So that's actually the velocity. Negative 1.00 meters per second I hat. I know I've written that really small, so I'm going to write it again here. The velocity of the river relative to Earth is negative 1.00 meters per second in the I hat direction. Okay. I'm going to say the velocity of a boat is actually, let's say, 12 meters per second. But of course, the boat can go at any angle it wishes. So what I would like to know is if the boat is parked right here, and this river, of course, is way bigger than the boat itself, I'm going to say this river has a width W equal to 300 meters. So nearly 1,000, or about 1,000 feet across, right? One thing I could ask you is what velocity should the boat travel at? Assuming it's going to go max velocity, what angle should it travel at to land directly across? So the boat equals question mark for this one. And then I'm going to say if VB, so this is part A, if VB is equal to 12.0 meters per second in the J hat direction. So I'm saying my x-axis obviously is this way, and I'm saying my y-axis is this way, like that. Okay. If the velocity is 12.00 meters per second, where will it run aground? How long will it take? Okay, so that's a pretty good relative velocity equation. Okay, so with this one, we're going to find out what velocity should I travel at to make this thing land right there. Well, I think you can look at this as a vector addition problem, and you know that the velocity of the boat as seen by Earth has got to be the velocity of the boat as seen by something plus the velocity of that something as seen by the Earth. That's the way our relative addition of velocities work, right? Well, I happen to have a velocity of the river with respect to Earth. So if I put an R there, then I'm only required to put an R here. So I just need to find the velocity of the boat with respect to the river, which I know in general, but I don't know. I mean, I just know the magnitude of it. I don't know what angle, right? What I want, though, is the velocity of the boat with respect to the Earth to be at an angle of 90 degrees. So I want VBE to be at theta equals 90 degrees. So if I set this up where the total velocity of the boat with respect to the river is 90 degrees, then that means the entire y component of velocity should be 12 meters per second, and it should have 0 x component of velocity. So this implies VBE sub x is equal to 0, and VBE sub y has got to equal 12.0 meters per second. And that's because I'm always going to run at 12.0 meters per second, right? But what I know is VBE is the final result. What I don't know is the velocity of the boat with respect to the river. And that's what we got to sort of work out, if you will. Okay. So I know that VBE, which should be 12.0 meters per second in the I-hat direction, has got to equal velocity of the boat with respect to the river. That would be velocity of the boat with respect to the river times cosine theta. So in other words, if I said the boat took off at an angle theta like this, then the x component would be VB cosine theta I hat, and the y component would be VBR sine theta j hat. But then I have the velocity of the river with respect to the Earth is minus 1.00 meters per second in the I hat direction. So just writing that, I think you can start to see something. Well, I know since I wanted to go purely straight across the river, I needed my total velocity to only have a component in the y direction, which I wrote here for some reason in the I direction. Hopefully someone caught that and changed it in your own notes. If you didn't, remember that's got to be purely j, okay? Because theta equals 90 degrees means it has no no x component, it only has a y component. So that should be the j. I think that shows you that this I component and this I component, they have to add to give you what? If the left-hand side only has a j component and the right-hand side has two I components, what do the two I components have to add to give you? Y'all can type it if you're shy. Okay, it has to be 0. There's no I component over here, so there can't be an I component over here. So I've got one equation, velocity of the boat with respect to the river times the cosine of the angle theta. And that's really what the driver is going to aim his boat at. So he's going to set it up such that this compass reads the angle theta and he'll be good. VBR cosine theta minus 1.00 meters per second is equal to 0. That's one equation. And then the other equation is VBR sine theta, which is the j component, has to equal 12.0 meters per second. I can solve one in such a way that I get VBR cosine theta is equal to 1.00 meters per second. I'll call this 1 prime. And then this is equation 2. If I divide equation 2 by equation 1, actually 1 prime, then I get Notice when I divide them, it'll be VBR sine theta over VBR cosine theta. This is a technique that you normally don't learn in your algebra class. You can divide one equation by another equation. You always got to watch out for whatever's in the bottom has a possibility of being zero. Then you got to avoid that scenario because you could actually get an equation that's not true. In this case, it's going to be 12.0 meters per second over 1.00 meters per second. Notice the VBRs cancel out like that. And sine theta over cosine theta is tangent theta. So I know theta is equal to the tangent inverse of 12.0 over 1.00. So if I take the inverse tangent of 12, I get 85.24. 85.24 degrees. That's 3 sig figs divided by 3 sig figs. So I really should be rounding it at this decimal place. Since that was not a 5, if this would have rounded to 5, I would have carried the extra digit just so I wouldn't like doubly round up. So if this was like 4 followed by a 6, that would make that a round to 5. And I'd want to keep at least that digit. So if I put a 5 there, then that would make me round this up again, even though I shouldn't have because it was a 4 here. So in that case, I would write 4, 6 instead of putting 5 there because it would let y'all know that you don't want to round that a second time. So now I know the angle. Now that I know the angle, I can plug it back into either one of these and find out what the actual angle is, or excuse me, what the actual VBR is. So now I know VBR will equal our VBR times the sine of 85.24. Again, I'm carrying at least that extra digit. You could probably carry another one if you wanted, or more if you wanted. That's supposed to equal 12.0 meters per second. So VBR is actually going to be a different velocity than 12 meters per second. The boat captain is going to actually floor it so that he gets the full velocity out of it. And it's going to end up going in a different direction than he had planned on going. Or if he worked it out ahead, he will go in exactly the direction he's planning on going. But he's not going to go the angle that his bow is pointed at, in other words. So what we're going to find now is that 12 divided by the sine of 85.24 degrees is equal to 12.04153. So 12.04153. This is 3 sig figs divided by a sine of 3 sig figs. So that should be 3 sig figs. So I really should be doing only 3 sig figs. So all these guys are extraneous. Okay. So it really should be 12 meters per second. So the velocity of the boat with respect to the river should in fact be 12.0 meters per second at, since that's measured counterclockwise from the positive x-axis, I can just say at and write down 85.2 degrees. And of course, you know exactly what that is in terms of x and y components. You know it's going to be 12.0 meters per second times the cosine of 85 point such and such. So 12.0 times the cosine of 85.24 I hat plus 12.0 times the sine of 85.24 degrees j hat, which equals
Can you
1, 2, yes. I'm off the screen again. Thank you. 12 times cosine 85.24. That gives me 0.99. That basically gives me 1. It's 0.9958, which obviously you can see rounds to 3 sig figs, should really round to 996, which is essentially 1 meters per second in the I hat direction. And then the 12 times the sine of 85.24 is 11.9586. So plus 11.9586. Again, that should only be the 3 sig figs, meters per second, j hat. So that's the two ways of representing the final velocity. I mean, the velocity that has to go. Basically, what you would do is if you're looking at the line and the boat, like this would be the bow of the boat. This would be the keel. This would be the stern. That keel should have a compass heading of basically, if this is due north, it should have a compass heading of about 4.8 degrees. That way. And by driving that way, it's going to look weird because he's going to be doing this, but he's got an x component of velocity that just happens to cancel out that 1 meter per second velocity in the horizontal direction of the river. And by keeping it aimed that way, he'll arrive across the river directly across from where he was. Now, if he blindly just did the velocity of 12 meters per second and shot at an angle theta, what's going to happen is he's going to travel at 12 meters per second this way, but it's also going to have a resultant velocity of 12 meters per second this way plus 1 meter per second that way. So for part B, we have the velocity is equal to 12.0 meters per second in the j hat direction minus 1.0 meters per second in the I hat direction. That's his real velocity. I've got to figure out how long it's going to take to go a distance of 300 meters. So x equals x0 plus v bar t for a constant velocity. The v bar is just plain v, and the x0 is just going to be 0. So what I'm going to get is that t is going to equal x over v. So the time, which is one of the things I asked for, as you can see up here, how long will it take and where will it run aground? The time is just going to be 300 meters per second, or excuse me, meters, divided by 12, almost right, 1.2, 12.0 meters per second, and 30 divided by 12, you could actually work out that math in your head. 3 goes into 12 4 times, and 3 goes into 100 300 3 times, or excuse me, 100 times. So 100 divided by 4 is 25. So this is 25.0 seconds is how long it takes to get across there. So that's one answer. And that, in some sense, is a little bit sort of the faster way because you're using all your velocity to go horizontally, or excuse me, to go vertically straight across the river. So that's sort of the fastest route you can really follow. If you want to know the other part of the question, which is where will it run aground? Well, during that 25 seconds, it's going to drift 1 meter per second to the left. So I know that it's going to move. Its x is going to be equal to x0 plus v bar t again, but this time I'm really doing it in the x direction. This one was in the y direction. So in the x direction, again, I want to take x0 to be 0, and this time it's going to be the river, which would be 1.00 meters per second. So I'm going to get x is equal to negative 1.00 meters per second times 25.0 seconds. And you'll see that the x is actually equal to negative 25.0 meters. So what's going to happen is it's going to go this way 300 meters, and it's going to go this way 25.0 meters, and that's where it's going to land. So it will run aground 25.0 meters. If I'm calling this north and this south, east and west, it's going to run around 25 meters west of directly across. Okay. And I think that's all I asked. I asked how long and where will it land. So yeah, that works it all out. You might notice that this component is what happens when you ignore the river component, the x component of velocity. The other ones, when you try to do the opposite of ignoring it, so that you're actually sort of canceling it out, you're really canceling out the ability to move 25 meters in that sense. So in some sense, this angle should be pretty close to the angle you actually had to fire. So if you took 25 divided by 35 and take the inverse tangent of it, let's see what we get. 25 divided by 300. I don't know. I think I said 335 for some reason. Now I take the inverse tangent of that. I get about 4.76, which is 4.8. So remember before I said I want a compass heading of 4.8 degrees this way. We end up moving over about 4.8 degrees to the left. Again, so that does, give you some confidence in the answer, because what I estimated would happen did happen. Any questions on that? All right, well, we are done with chapter 20, excuse me, chapter 23, with chapter 3. Next week, we'll go ahead and jump into chapter 4, which is Newton's laws, and we will do chapters 4 and 5. And if you'll notice, I have my weeks opened up, so you can start looking at videos of what I did in the past for this corresponding stuff. You also see that I already have some videos up. For kinematic motion, I did a car chase one, which I think might have been one of the homework problems. I did something like one of the homework problems that's a car chase. And I did some other kinematic equations too, just to let y'all see how to use the kinematic equations. So by all means, be checking out my YouTube channel. I haven't added anything new to it recently. So if you decided to subscribe to it, which I hope you do, because it will help me ultimately have an easier URL. I have a URL I own. It's physicssolutions.com. I would like to actually use that for the URL, but once I get, I think I have to have 100 subscribers and they have to watch 400 hours. Once I reach that point, then I can use my URL. So hopefully you guys will subscribe. Y'all can cancel it later, or you can, if I put too much stuff one day, just unsubscribe then. But it would really help me out so I could make the address a lot easier. Anybody has any questions, stick around. Other than that, you're free to go. I will see you at 12:45 for lab. We're doing analyzing motion graphs. Diego, do you have any questions? All right, I'm assuming he didn't exit, so